Okay. Hello. My name is Che. I'm from Northeastern University, and today we're going to start with part three of neural networks and clustering. In the past, we've talked about autoencoders and how to combine autoencoders and k-means. Today, we're going to move on to another paper that essentially combines autoencoders and spectral clustering. So, in 2014, Tian et al., I think it was in Triple AI, published a paper called Learning Deep Representation for Graph Clustering. And like I said, they essentially, not exactly, but they did autoencoders and spectral clustering, which they actually use a restricted Boltzmann machine, but I'm going to show it. The idea is very similar, and I'd rather show it through the concept of autoencoders, since we've already done it already, and we know what autoencoders are. So all we really need to understand is spectral clustering, which I have previously in a different series gone through the idea of spectral clustering. So as long as you understand spectral clustering, it's pretty easy to go over autoencoders. And today I'm just going to go over the basic mechanics of spectral clustering, right? So how does spectral clustering work? First, given some data x in some dimension e and with some dimension d and n number of samples that looks something like this, we generate some kind of this thing called a similarity matrix, okay? W, which is an n by n matrix. And each element in this, like let's say this one, Wij, actually tells us the similarity between xi and xj. So this one, for example, W12, tells us how similar they are. And if they're similar, it also implies that they should belong in the same cluster. So if they're similar, like if xi, and xj is similar, then Wij should be large. And if they're very different, then Wij should be small. So you can picture, since there are n of them, the matrix will be n by n because it's matching up every one with every other one. There are many ways to calculate this Wij, and the way we calculate them is through this function called the kernel functions. And the most popular one that most of you would use will be the radial-based kernel, or the RBK, also known as the Gaussian kernel. Now, if we have two samples, xi and xj, well, when we have xi and xj, the function looks like this. We put xi in here, and this essentially, and we just have to do that with every single combination of ij, and that gives us the W matrix. This function right now, this function, if they're very close, xi and xj is equal to each other, so close they're equal to each other, this will become 0, and this right here will become 1. So if two samples equal to each other, I mean, you can't get more similar than that, right? And you will get a large number. Now imagine if they're very far apart from each other. So the difference between them is like infinity. And when it's infinity, we're going to get a 0. So you can see when things are far away from each other, we get a 0. And when they're close by, we got a 1. So this is a good way of measuring similarity and good way to calculate this Wij. So we start with the data. For every combination of I and j, we calculate Wij. It's pretty simple, just pure mechanics. And after that, once we get W, we compute this thing called the degree matrix. Degree matrix. D, which is very simple. We have D1, D2, D3, it keeps going. And D1 is literally, you just add that up and that's equal to D1. You add this up here, that equals to D2. Depending on the size, it could be very big. So you have lots of D's. And everything else is 0. So you can see, this is how you calculate the D's. Now, The degree matrix, you can picture it as a way of telling us the size of a similarity matrix. If this is large, obviously this is large. So it's kind of like a summary of its like volume. How big is it? Well, you can use D to measure. Next, we use this matrix called normalized Laplacian. Now, the way we calculate the Laplacian, we just take W and divide it by its size. So you can kind of picture we're normalizing this W matrix. Very often, we could just use the W and it will work for a lot of cases. But we like to use the normalized version because it tends to perform better. So next, so right now we're literally just going through the mechanics. Like I'm not going through why we do this, but the mechanics is what you need to understand what this paper is doing. Next, we do this thing called spectral embedding. It's pretty easy. You have a matrix L, and we find an eigenvector, and we kind of sort them up such that the eigenvalue here is greater than the eigenvalue here, greater than the eigenvalue here, and so on and so forth. So we take the eigenvalue and sort the corresponding eigenvectors, like here. And then, depending on the number of clusters, K, so let's say we have 3 clusters, right? 3 clusters. 3 clusters. We pick the number 3, most dominant. So we chop off, like right here, like chop it off right here. And this right here becomes the spectral embedding. So only 3 of them. So like you can see, doing the spectral embedding, the result is just the 3 most dominant eigenvectors. And this becomes an M by K matrix. And the final step that you need to know, k-means on this. So there are n samples, and we treat each row as if it's a sample. And we run k-means on it, which give us the y that we want. That essentially give us the clustering designation. So in summary, we start with some data. Through some Gaussian kernel, we calculate the W matrix. From the W matrix, we add up each row, and that becomes the degree matrix. We normalize the W matrix, which gives us the L, the normalized Laplacian. Next, we do this thing called spectral embedding. So normalized Laplacian is like this kind of a big matrix, and after this, we create a small one. And lastly, we perform some kind of k-mean on this that gives us the y. Well, at this point, if you have not seen my spectral clustering videos, you should go see it if you're interested why this works. Now, you know the mechanics of this now, but you probably, if you haven't seen the video, know why. And if you're interested, well, long story short, go watch the why. Re-explaining that will take quite a few videos. So it's better off that you just learn how spectral clustering from the series itself. But as long as you understand this mechanics right here, I can tell you what this paper did. So in Tian's paper, the key is this part here, right? This part, the spectral embedding. So everything else is actually the same. They revised this portion. We know that L is an M by N matrix, and V is an M by K matrix. So spectral embedding is a linear way of compressing the data. You notice what it did, it compressed the data. An autoencoder is a nonlinear way of compressing the data. So instead of using the eigendecomposition, which is what spectral clustering did, from here, the big one to a small one, used through eigendecomposition, what this paper did is that it used, well, RBKs, but for our case, they used autoencoders. So you can picture this was a big one, and then they take the bottleneck, right, and create a new set. which is much smaller. Once they get the new set, right? Once they get the new set, here it is. So they go from a big matrix to a small matrix, and then everything else is the same. Here's the same, here's the same, they're all the same. So that's it, actually. As you can see, Autoencoder has been like real big key to clustering. That's why I started the video series with autoencoding. And I think that's it for today. And in the next one, like, I'm going to talk about the latest that I read. I think it was NIPS. I don't really know for sure, but Deep Subspace Clustering Net. Yeah, you're going to see a pattern here. Essentially, they use autoencoders. So I guess I will show you this in the next video. All right.